Hello everyone, this is chapter 6.5 where we'll be discussing the average value of a function, and this is the last section, believe it or not, for chapter 6, so that's good. And as it turns out, this is a pretty simple topic. Now the average value of a function f on the closed interval a to b is given by f_av for average, 1 over b minus a, that's the difference in the interval endpoints, so that's the length of the interval really, multiplied by the integral from a to b of f of x dx. Now, why this is the case is actually pretty simple to explain. So, this is our usual image for the area under the curve of f from a to b. We have the x-axis. The y-axis could be anywhere. We really don't care. And notice that this, of course, is the area. Okay. So the average value of f would be the average height. So how can we find the average height of f? Notice some heights are larger than others. This height's larger. This height is the lowest. So where is the average height? Well, one way to discuss average height would, instead of looking at this image, kind of look at this image. So they're not the same, but they kind of compare. So let me write this kind of tilde here. And let's compare to this image, which is very similar looking, only instead of from a to b under the curve f, let's look at under some straight line, which is y equals something, y equals some number. Because every horizontal line has the equation y equals a number. And we want this so that the areas are actually the same. So that this shaded region is actually the same as that shaded region here. So let me just label them as both being A. So, what can that y value possibly be? And also, why do we want this to be the average height? Because this basically represents that height in some sense, because the areas under are the same. We're not changing the width, we're just changing the height. So the areas are the same, so we'll actually end up getting the average height, which is just this y value. Now how we can find this y value, well, it's here. But really what we can say is, if you call it f_av for average value, what you'll notice is that the area under the curve is equal to a, and in this case, the area under the curve, of course, is just equal to the height, f_av, multiplied by the length of the interval, which is, of course, b minus a. Now, of course, if you divide both sides by b minus a to solve for the average value of the function, you get 1 over b minus a times the area. And notice that this integral is indeed this area a that we're talking about, because they have the same area under the curve. Only here it's a straight horizontal line, and here it's an actual function. So that's the main idea. Now, average value actually does correspond to average, like mean average. So that's when you add up all the values in a set divided by the amount. Here it's harder to say that because it's a continuous function. We don't have finitely many values. We have infinitely many values between a and b, but this is how you would find the average of values that follow a certain distribution or follow a certain function, you would say. So that's more into probability, and I'm not going to discuss that too much in this section, but at least it gives us an idea of what, as far as what's going on. And in fact, this topic is used, or this idea is used a lot when discussing things. For example, let's say the temperature throughout the day, let's say it goes from 72 degrees to 80 degrees, anywhere in between those, and it follows some certain curve, and you can kind of find the temperature at each particular second, let's say, or minute or something like that. And then it follows some curve. You find the area under the curve, divide by the length, and that'll give you the average height or average value. So that idea is used a lot. That's just a particular instance of that. Anyways, now moving on to this example, let's see what's going on. So we want to find the average value here, which we'll call, of course, f_av. And by the formula here above, which is really all we're using here in this section, is going to be 1 over b minus a, here's a and here's b. So b minus a in this case will be 2 minus negative 1, which is actually just 3, times the integral from negative 1 to 2 of our function 1 plus x squared dx. Now, of course, that number is 1 over 3. The antiderivative of 1 plus x squared is, of course, x plus 1/3 x cubed. Evaluate this between negative 1 and 2, and then we're done. Now, when we plug in 2, we get 2 plus 8/3, because 2 cubed is 8, so it's 8 over 3. That's the first evaluation, minus, when you plug in negative 1, you get negative 1 minus 1/3, because negative 1 to the third power is negative 1, and then multiplying these by 1/3. So now if we distribute this, we'll get positive 1 plus 1/3. So let me just write that here down below. So plus 1 plus 1/3. Notice these actually combine to 9/3, which is 3. So we get 1/3 outside of. If you combine these, that's 1 plus 2 is 3. And then plus 9/3 again, which is also 3. Look at that, you just get 6/3 because it's 6 times 1/3, which is 6/3. And that's actually 2. So what a nice looking answer. So the average height is 2. And if you want to visualize this by actually graphing, you can do that. I'm not going to do it. I guess I will do it. Fine. You convinced me. So going from -1 to 2 under the curve, 1 plus x squared, which is of course just a parabola shifted up 1 unit, so it's y equals 1 plus x squared. There we go. So now when you plug in 2, you get 2 squared plus 1, which is 5. So this is 5 and this is 1. So this is of course not to scale. To make it look a little more to scale, 1 should be about here, something like that. Sorry, I just want to get the image right. That looks a little better. Perfect. Well, not really perfect, but close enough. Okay, so now the average height is then, so that's 1, and then 2, 3, 4, 5. Perfect. So this right here is the average height. So that's y equals 2. Let me just call it f av equals 2. So what that says again is that the area under the curve of this kind of ramp-looking shape, the parabola between -1 and 2, is the same as the area from -1 to 2 under this horizontal line, y equals 2. Awesome. So now we'll move on and discuss a new idea that will have this, well, it has to do with this, and then from there we'll do a few more examples. Alright, so the next idea I was talking about, of course, is called the mean value theorem for integrals. So yes, it is the idea of mean value theorem coming back to us, which we saw in 4.2. And the mean value theorem was kind of a weird theorem because we didn't really see too much use of it. In fact, we still won't really see too much use of it, but that idea still is kind of here. So it says the following. It says, if f is a continuous function on the closed interval a to b, then there exists a number c in that interval a to b, so some number in between a and b, such that this holds. So we box this. And it says f of c, f of that number, is equal to the average value, which we know is the 1 over b minus a times the integral from a to b of f of x dx. So that is this. So we're just multiplying both sides by b minus a as to clear fractions. So this last part isn't as important. I actually like this statement better. But now what this really says is that if you have a continuous function, and I guess we don't need the y-axis again. If you have a continuous function like this, then the average height must be in between these heights. So if this is f, and like this is a and b, let's say, it must be the case that f average is somewhere in between these heights. And we know that because, like I mentioned earlier when we described f average, it's the average height. So it's somewhere in between the lowest height and the tallest height. So what that means is that if f is continuous, then there exists some value. I made it look like it's a midpoint, but it may not be. In fact, it looks actually like there's 3 values here, but there exists at least one value, such, let's call it c, such that f of that value is equal to f average. So when you plug c into f, you get the average value. Good, so that's all it really says. And if you look back at the actual statement of the mean value theorem, it's something pretty similar, only the original mean value theorem from 4.2 has to do with derivatives, not integrals. Anyways, with that being said, let's find the actual value c for which this happens with the previous problem we looked at. In fact, we even graphed it. The graph I showed you, I don't think was actually to scale. And in fact, I made it look like there were 2. There, I think, are 2, but maybe I'll graph it afterwards. But for right now, let's just look at this algebraically, so non-graphically. So the first step to do is to find the average value. Well, we actually did that already, so you can recall from the previous example we did. We found that that's just for this, and it ended up being 2. So now we're going to say that by the mean value theorem, there exists a c such that f of c is equal to 2. And this c has to be in the interval -1 to 2. So remember that symbol means in. So c is in this interval. So we only want to take values that are in between -1 and 2. And what is c? Well, we don't know what c is, but what is f of c? F of x is 1 plus x squared. So that means that f of c is 1 plus c squared is equal to 2. So of course when you subtract 1 to both sides, you get c squared is equal to 1, which implies that c is plus or minus 1 when you take the square root. And both of these values are actually in this interval, so those are our values. So just to write in as like a comma separated list, it's c equals -1 or c equals +1. And I'm going to show that though by graphing. So I'm going to try to make this a little more to scale than I had the previous one. So it's 1, 2, 3, 4, and we need 5. And the reason why we need 5 is because that is the highest y value we obtain. So remember the parabola looks something like this. When you plug in 1, 1 squared plus 1 is 2, so it's going to be this value here like this. And when you plug in -1, you also get 2. So these are actually where you hit the average value. So that's kind of all we need to say, but I'm going to show you the actual complete image, if you will. When you plug in 2, that's 2 squared plus 1, which is 5, as we saw previously. So we end up getting this. If you extend this, is like that. Awesome. So that right there, that's the area under the curve. If I were to shade this, and let me show in red, this line that passes through y equals 2, well, the line y equals 2, that is the average value. So that's f average. And notice there are two values where we get actually an intersection, which is at c equals -1 and c equals +1, or I guess x equals -1 and x equals +1. Great, so we showed it graphically too. And again, the reason why this is the average value is because the area under the curve of this box is the same as the area under the curve of this shaded region, which I'll shade in black. Awesome. So now we'll do one more example, and I think that's actually going to be it for 6.5. Right, so I said we'd do one more problem, and it's going to be this one really, but as a bonus, I want to try to do this problem, which is not really the type of problems we were doing from the previous screen involving the mean value theorem, but this does involve the mean value theorem, but it's more physics applied, so I think it'll be fun to look at this as an afterthought to finally conclude 6.5. But let's get on with this one. This one's going to be a little challenging for us, so let's see. So we want to find f of c such that it's equal to the average of this function on this interval. So first let's find the average, which is of course going to be 1 over the difference of these endpoints, which is just pi minus 0 is pi, times the integral from 0 to pi of this. I'm going to do this a little quickly. We need kind of a u substitution for the second one, but let's see. Antiderivative of 2 times sine is -2 cosine. Of course, because antiderivative of sine is negative cosine. Here we kind of need a u substitution because it's of 2x, so you can let u equal 2x. Do that on your own. You'll see what happens. Basically, since u is equal to 2x, then du must be what? It must be 2 dx, so that 1/2 du is equal to dx. And then you'll get the integral of sine of u, which is negative cosine, but it's a double negative, so it's really positive cosine. But then you get this 1/2 coming out. So long story short, this is plus 1/2 cosine of 2x, because then you back substitute. Now, the way I kind of see this ahead of time is that our inside is a linear function. So that means when you antiderive, take the antiderivative like usual, keeping the inside the same, but since your derivative of the inside is a constant, then we're going to have to divide by that on the outside. And it makes sense because when we take derivative of cosine of 2x, the 2 comes out, derivative of cosine is negative sine, so the 2 that comes out from chain rule cancels this 1/2, and you indeed get negative sine of 2x. Perfect. So now we need to evaluate this between 0 and pi, which will be fine. But then not only that, we have to multiply this by 1 over pi still. So let me just kind of squeeze that part in, and we're off. Great. So now let's do this evaluation. It's going to be pretty quick, I think. When we plug in pi, cosine of pi is -1. So we're going to get, let's see, that's going to be 2 times -1 plus 1/2 times cosine of 2 pi is +1. That's the first evaluation. Minus the second evaluation, -2 times cosine of 0. Cosine of 0 is actually +1. Plus 1/2 times cosine of 2 times 0, which is still cosine of 0, which is still +1. So that's kind of interesting. And notice we're still multiplying by 1 over pi on the outside. Great. And this is only half the problem, because after we find the average value, we need to find out what value c is the case such that f of c is equal to this average value. So I may need to clean up just for space after we find this. But we're almost there. Notice this is +2, that's +1/2. After distributing this is -2, but after distributing you get +2, and that's +1/2, but after distributing you get -1/2. These cancel out, so we end up getting 4 times 1 over pi, which is 4 over pi. So now I'm going to clean this up, write that answer here, and then we'll continue this problem. Right, so now this is what we got. I cleaned up everything. We got f average is equal to 4 over pi. And I think we're really in for a treat here. You can just kind of tell a little bit ahead of time. We want to find f of c. We want to find c such that f of c is equal to 4 over pi. That's what the statement's asking us to do. So let's see, what is f of c? Well, f of c is 2 sine of c minus sine of 2c. Now, instead of writing sine of 2c, I'm going to use the fact that sine of 2x is equal to 2 sine of x times cosine of x, and that's just a double angle formula identity for sine of 2x. Good. So I'm going to replace that with 2 sine of c times cosine of c. Hope that double c doesn't get us confused too much. And that's cosine of c, sorry. There we go. Equals 4 over pi. Whew. Nice. So far so good, I think. But why did I need to do that? I think the reason why I needed to do that was so that we can see that we have these two sine of c's in common. So we factor that out. Let's see what happens. Factoring out 2 sine of c, sometimes this is helpful to do. On the inside, we get what? We get 1 minus cosine of c, but this is equal to, so I'm wondering if this is going to help us at all. So this is equal to 4 over pi. Doesn't really seem to help too much at all. In fact, maybe there's no other way of going about this, but replacing cosine with something in terms of sine. So the way you solve these kind of trig equations is to get everything in terms of the same function. Now here it's sine of x and sine of 2x. They have different arguments, so that's why things got a little crazy. But here, let me just think for a second. And we're still okay. So here, then we have both of these in terms of sine, but then we have this cosine. It kind of confuses the issue. Something that I want to use is the fact that cosine squared of x is equal to 1 minus sine squared. But then, see, the problem there is that when we actually find cosine of x like this, you get a square root, and even worse, you actually get a plus or minus square root. So that's something we could do if we absolutely need to, but I think that gets a little too crazy. In fact, just to kind of show you what it leads to, let's try to do that here. So if we replace cosine with this, again, it's going to be plus or minus, so we get 2. In fact, we can just divide both sides by 2 straight up. So we get sine of c minus sine of c times the square root of 1 minus sine of c squared. So it's c sine of c, 1 minus sine of c squared, which is like this. There's a plus or minus times this radical, so it really makes this minus plus. Minus plus is the same as plus minus, only your plus case is a minus case. That part doesn't really matter. But again, we're dividing by 2, so 4 divided by 2 is 2, so we get 2 over pi. And now if we replace sine of x with, well, I guess sine of c, if we replace sine of c with x, then we actually get an equation involving x that is doable. So let's see what this, again, is a little crazy. we get x plus minus the square root of 1 minus x squared. Sorry, x times 1 minus, there we go. X times radical 1 minus x squared equals 2 over pi. All right, so how can we solve for x in this crazy equation? Well, we have these two scenarios here, but in reality, we want to get rid of the radical first. So I can subtract this to the other side, maybe divide by x and then square both sides. Dividing by x is actually not necessary. So we can just isolate the part that contains the radical by subtracting the x to the other side, and then we have to square both sides. Now, of course, I'm missing the minus plus part, so I'll include that, but when you square it, the sign doesn't actually matter. So when you square this out, you get x squared times the radical squared, which cancels the radical. When you square this out, you get a binomial squared. That's going to be 2 over pi quantity squared, which is 4 over pi squared. Minus 2 times the product, which is negative 4 over pi x. Plus the last one squared, which is x squared. Now we can distribute this, move everything to one side, and try to solve this. This is looking really nasty because it seems to be a quartic equation that involves x to the 4th. So the only real way I know how to solve this at this point really is, well, to kind of use some type of graphing. Well, let's just see what happens. So we get x squared minus x to the 4th equals 4 over pi squared minus 4 over pi times x plus x squared. Notice you can subtract x squared to simplify this a bit. But yeah, this is not going to happen because this type of problem is way too complicated to solve. The only way I know how to do it really is by using something like intermediate value theorem, or maybe Newton's method if you want, but that's going to take way too long. You can do it though, and you'll get an approximation for a value, and make sure that value is in between 0 and pi. So in fact, using IVT or Newton's method with a guess in between 0 and pi wouldn't be a bad idea. I'm going to do that off screen, and then I'll write down the result. Okay, just a full disclosure, the way I solved this problem, or at least the way I got to this equation, squaring both sides, generally can lead to extraneous solutions. It didn't in that case because we still had the plus or minus in the original equation involving radicals. In fact, here this one solves, or is a solution to, I should say, the positive case, whereas this is a solution to the negative case. Now, these are the x values. We want to find the c values. So also, I kind of misspoke earlier too. I said that we can use Newton's method or IVT using this interval as our guess, but actually this is our interval for the c values, not for the x values. To find the interval for the x values, you can just plug these into c to get your interval, or the endpoints of your interval anyways. So notice in that case, it would be sine of 0 and sine of pi, which is just, well, that's 0 to 0, which sounds kind of weird. But since psi can be at most 1 in between 0 and pi, then really we're looking at x values between 0 and 1. And in fact, I really did this graphically, and I got these to be our solutions, and they're valid x solutions to this equation. In fact, if you were to graph this, it looks something like this between 0 and 1. It does kind of like this dip here. And it's a kind of upward shape always, but it touches here and here. Awesome. Now, what the c values are then are just applying sine inverse to this. There is a little bit of a problem though. When you take sine inverse of a value, the range of sine inverse is in between negative pi over 2 and positive pi over 2. So really this is only going to give you solutions in the first or fourth quadrant. Since they're both positive, these are both solutions in the first quadrant. But 0 to pi, that's in the first and second quadrant. But that's okay because notice that sine on the unit circle in the first quadrant is the same as values in the second quadrant that have the same reference angle. So if this angle is theta, then this angle here would just be, well, that angle would be pi minus theta. Because if this angle is also theta, which would correspond to the same y value, because sine is the y value on the unit circle, then if theta doesn't work, then pi minus theta must work. Now, what I mean by work is I mean by when you plug this in to our function, we get our average value 4 over pi. And here, this one works. This one, we get that actually. If you try the other value, which is pi minus this, pi minus 2.3, which the value escapes me at the moment, but if you approximate it, you'll get something. When you plug that into this, you don't get about 4 over pi, so that doesn't work. Also, 0.333, which is sine inverse of this first value, doesn't work, but its complement, so its angle that corresponds to the same reference angle in the second quadrant actually works, which is pi minus 0.333, which is about 2.81, I'd say, something like that. In fact, I'll tell you right now, it's 2.815 if you round. Okay, so good. So these are the two C values that do it, and that's where I'm going to stop this problem here. Let me just box my answer. So 2.815 or 1.238. So this was obviously a very, very, very complicated type of problem. But at least it shows you the process, and the previous problem showed you the process too, but that was kind of simple. So yeah, I didn't really show any intermediate examples. This one is still kind of doable, maybe. I don't know. I say this is a little extreme, to be honest. It involves a lot, but you know, it's a good way to end chapter 6. So I think that's fine. Now, finally, like I said, this is mostly an afterthought, but we want to show that the average velocity over the time interval t1 and t2 is the same as the averages of the velocities during this interval. Now, the averages of the velocities will be the average value of the velocities. So that average value, let's call it VAV, is actually going to be 1 over the length of the interval, so that's t2 minus t1, of the integral from t1 to t2 of the velocity. So the velocity you can call v of t. So if we know the velocity function v of t, then we're good to go. Now we want to show that this is equal to the average velocity. Now average velocity, which kind of looks like this, it's kind of funny. So it has the same notation, but let's call it v bar, which is usually used in physics sometimes. And that's going to be, of course, the change in the distance, let's call it s, over change in time. Now the change in time here will be, of course, t1 or t2 minus t1, just the difference in the time stamps, I guess you can say. And the change in the distances is, of course, going to be, let's call it s2 minus s1, which are just the distances at those time values. So maybe it's best to call those s of t2 and s of t1. That sounds a little better. So we want to show somehow that this is equal to that. Now we have this denominator part, which is clearly the same already, fine. The integral part, how can we show that's the same? Well, actually what comes into play here is that the derivative of the distance function is actually equal to the velocity function. So now that we have that, the derivative of the distance function is the velocity function, which is an idea we saw a lot in early on in this class. That means the antiderivative of v is going to be, well, s plus a constant, but for for definite integrals, you don't need that plus c. So in fact, this is really equal to 1 over t2 minus t1 times the derivative of vt, which is s of t, evaluated between our t values. And that's actually it, because when you evaluate those between, or when you evaluate s of t in between those t values, you end up with 1 over t2 minus t1 times s of t2 minus s of t1 by ftc part 2, and that is actually literally just this. So we've shown what we needed to show. Awesome. So first off, I want to thank you all for having patience with me with this problem, because I know I kind of went a little bit off the edge there. But aside from that, this was a pretty fantastic showcase of what average value has for us. And this is a nice finale for chapter 6. So the next thing really to do would be to enter chapter 7. So if you want to take a look at that, I have videos up for chapter 7 already. So I'll see you in the videos for that. Hope you enjoyed this. Thanks for watching, and I'll see you then.